Problem number 1. For this problem, we're given this vector field, f right here, and C is the oriented closed curve between 1, 0, 0, 0, 0, 1, and 0, 1, 0. 3 straight line segments is C. We're asked a bunch of questions here. Part A is the curl of f. Okay, I hat, j hat, k hat. I always write this out as a determinant of a 3 by 3 matrix, thinking of this as a cross product. And so x squared minus 2y, y squared minus 2z, and z squared minus 2x. Okay, so the I hat component will be the partial derivative with respect to y of this. There's no y dependence, so that's 0. Minus the partial derivative with respect to z of this, minus negative 2. The j hat component will be the partial derivative with respect to z of this. There's no z's there, so that's 0. Minus the partial derivative with respect to x of this over here, minus negative 2. And finally, the k hat component will be the partial derivative with respect to x of this, which is 0, minus partial derivative with respect to y of this. So our curl ends up as the constant vector 2, 2, 2. So that's part A. For part B, we're asked to compute the divergence here. So we add up the partial derivative of the first component with respect to x. That's 2x, plus the partial derivative of the second component with respect to y, plus the partial derivative of the third component with respect to z. This is what we end up with. I'll just point out here, so this is a scalar quantity. That the common mistake here would be to write this out as a vector quantity. Okay, part C asks us to compute the line integral around f of, the line integral around C here. To do this, so we are asked to compute this right here in part C. And so I want to do this using Stokes' theorem. So Stokes' theorem says, well, we can relate the circulation of a vector field around the boundary of a surface here to the integral over the surface inside of here of not f, but the curl of f. And so let me write this down just a little bit. So this is what we're aiming for. But I usually want to, I feel most natural orienting D pointing upwards in the positive z direction. In this case, C is actually oriented in the wrong direction. C is oriented clockwise. For Stokes' theorem, in the statement, we are assuming C should be oriented counterclockwise. How do we fix that? I'm going to slap a negative sign on this, and that will take care of it. Okay, so let's proceed from here. We'd have to parameterize the surface D. And we can parameterize the surface D. So this is a little part of the plane. X plus y plus z is equal to 1, or z is equal to 1 minus x minus y. And so we end up with x comma y comma 1 minus x minus y, where here x can be anything from 0 to 1, and y can be anything then from 0 to 1 minus x. A normal vector, all right, so x cross r sub y ends up as 1, 1, 1. And so then we will be integrating, so our bounds, throw on the minus sign here, bounds x runs from 0, 1, y runs from 0 to 1 minus x of the curl 2, 2, 2. Dot product our normal vector 1, 1, 1 dy dx. And so what does this give us? Negative integral x runs from 0, 1, y runs from 0 to 1 minus x of 2 plus 2 plus 2 is 6 dy dx. And so this ends up as 3 if you crunch that out. Okay, so that is part C. For part D, we're asked for the sign of the integral around C of the, not f, let me write this correctly, but the divergence of f. So the divergence of f, let's write this down here from right there. It's 2x plus 2y plus 2z ds. This is actually a scalar line integral. This is a scalar line integral. And so the thing to realize here is that in the first quadrant, x, y, and z are all non-negative. So our integrand is always going to be greater than or equal to 0. In fact, it's not too hard to argue that this is strictly positive here. And so because the integrand is always positive, then this integral is positive itself. So that answer is part D. For part B, is f conservative? And the answer to that is no. Why can we tell that? The curl of f is 2, 2, 2. And this is not equal to the 0 vector. And so f is not conservative. If f were conservative, the curl of f would have to equal 0. Okay, that's problem number 1. Problem number 2 says, use Stokes' theorem to evaluate flux of the curl of f through where f is this vector field here. And the surface is going to be, let's draw a picture here. It's this cone. It's this cone right there. Okay, so how do we tackle this kind of problem? Well, we are going to want to use, we're told here to use Stokes' theorem. So the double integral over our surface of the curl of f dot ds is equal to the single integral around the boundary of our surface of f dot dr. So the boundary of our surface is right here. It is the circle x squared plus y squared is equal to 1 in the plane z is equal to 0. You can see that we'd have to set this equal to 0, and we solve this is equal to 0. That's x squared plus y squared is equal to 1. How do we parameterize this? R of t is cosine t, sine t, and 0. R prime of t is negative sine t, cosine t, and 0. What else do we need? We need f of r of t. We need to take our parameterization here and replace x with cosine t, y with sine t, z with 0. Okay, so we have x is cosine t, y is sine t, e to the 0 will just be 1. That's cosine t times sine t. X is cosine t, e to the negative 0 would just be 1. So that's just cosine t minus 0 times who cares. And a sine of xy times 0 will just be sine of 0 is 0. So there's our f of r of t. And then we compute f of r of t dot product with r prime of t. So this dot product this will give us negative cosine t sine squared t plus cosine squared t plus 0. So this integral ends up equaling, integral, of course, our bounds here, t runs from 0 to 2 pi, of negative cosine t sine squared t plus cosine squared t dt. To finish off this problem, I'll just comment here, when you integrate negative cosine t sine squared t on this interval, that will give you 0. And so at the end of the day, we just integrate cosine squared t here, and we'll have pi as our final answer.